This section is about how things can go backwards and forwards at the same time. So, you've taken sides in a battle between graffiti artists who specialise in making geometrical patterns on walls. You're trying to help one artist to up their game and roll a cylinder along the ground with a paintbrush attached to its end to trace out a pattern with loops. At the moment, they can only do humps. Mathematically, what you're doing is tracing out the path of a point on a circle, your cylinder, rolled along the ground, a straight line. This trajectory is called a cycloid and is a simple case of a path of a point on a curve rolled along the edge of another curve, also known as a roulette. Let's explore this in more detail by thinking about a wheel attached to a bicycle rolling along the ground. Suppose that the bike is travelling at a speed of 10 meters per second. How fast is the wheel moving? Sounds like a stupid question with an obvious answer. 10 meters per second, obviously. Well, not quite. The centre of the wheel is fixed with respect to the rest of the bike, so yes, it is moving at 10 meters per second, but the rest of the wheel is rotating about the centre to propel the bike forwards in the first place. To move the bike forwards at this speed of 10 meters per second, the edge of the wheel must roll over 10 meters worth of its circumference every second. So the velocity at any point on the edge of the wheel relative to the centre of the wheel must be 10 meters per second in a direction tangent to the wheel edge. What we've just described was relative to the centre of the wheel, but the centre of the wheel has the same speed as the rest of the bike, 10 meters per second forwards. So by using vector addition, we can calculate the velocity of any point on the wheel from the point of view of a stationary observer. When we add the vectors, we find that the top of the wheel has a velocity of 20 meters per second and the bottom of the wheel has a velocity of 0. A strange result, but true, and also good news for the wear on your tyres. The fact that the top of the wheel is moving much faster than the bottom explains the shape of the cycloid, which is smooth or fast at the top and spiky or stationary at the bottom. All good stuff, but this analysis still hasn't given us the loops that we're after. These loops represent motion, where the edge of the wheel is going backwards, even though the bike as a whole is going forwards. It's difficult to imagine how this might happen. A way in is to think about the velocity of part of the wheel at somewhere that's not the edge. The forward speed of the bike fixes the speed at which the bit in contact with the ground must go, 10 meters per second. And this fixes the rotation rate. The angular velocity omega is given by 10 divided by whatever the radius of the wheel is. Using the equation speed is angular velocity times radius, we can deduce that parts of the wheel which are nearer to its centre are moving more slowly, and parts of the wheel which are further away are moving more quickly. We've nearly solved our problem. Consider the wheels on a train. They roll along a track and a rim with a wider radius sits below. Think about the speed at the very bottom of the rim. It has a radius larger than the bit of the wheel that's in contact with the track and therefore a greater negative velocity too. So that even when we add on the overall speed of the train, the velocity at the edge of the rim is still negative. This, going backwards while the overall motion is going forwards, will give us the loops that we're after. How could you emulate this for your graffiti purposes? If a train is travelling forwards, the lowest parts of its wheels are always going backwards.